Okay, good morning, everybody. Today you're going to study transient response. This is an extension of the last lecture. Now you're going to quantify how well a system responds to a given command. We were looking at a transient response before and the overall time response of first and second order systems. And in this lecture, you're going to put metrics, put numbers to quantify how the system responds. How much overshoot do we see, how much time it takes to settle, and so on. So these are very important requirements when you design any sort of system. You want the system to react fast, and you probably have some constraints in terms of how much the system can overshoot. So that balance between overshoot and settling time, we can quantify using the metrics that we're going to see today. So this is lecture 18. We are approaching the final lectures. We had 24, so 3 more weeks. Lecture 19 is a lecture for practice exercises. There's no new content there. So I have that buffer lecture there in case you would like me to go over some examples of whatever we have done so far. So if there is anything specific that you would like me to show some examples and solve here, send me an email, or if you are at home, you can type that in the chat. Any lecture, particularly after the midterm, if there's any new contents there that you would like to see more practice exercises, just let me know, and then you're going to use the next lecture for that. Okay, you can either email it to me, or if you are in the chat, just type it. Otherwise, if I don't hear anything, then I'm just going to select topics that I think you are struggling with, or they are the most difficult ones. But ideally, I would like to hear from you to see what you would like me to do in the next lecture. Okay, so you're going to use the entire lecture then just to do some examples and no new content. And then lecture 20 will introduce the final content of the lecture, the final topic of the course. Okay, so let me know today, because I have to prepare for that lecture. Right now I don't have anything, and whatever you would like me to go over, we can revise it in lecture 19 on Wednesday. So back here, we are going to study transient response. The idea is to quantify how a system responds to certain commands, and or how we react to different types of inputs. So by the end of this lecture, you should be able to understand the concept of transient response. But we covered this before, but here we are going to take it one step further. We want to quantify, to put a number on, to characterize how the system actually responds. Recognize the relation between pole locations and the transient response, and analyze the transient response of a second and first order system. So let's go back to the example we had here. I don't know if this was the exact one, but if you have this satellite and you want to adjust the speed, the way it is done is by changing its moment of inertia. So here we have a mass that translates on that beam, and by moving that mass around, we are changing the moment of inertia of the satellite, and that will affect its speed. If you want to go from speed A to speed B, we may go from speed A to speed B slowly using an exponential, or if you want to go fast, the system may oscillate, may exceed the speed we want before it settles at the desired speed. So how can we determine this type of overshoot? This is one of the applications of the lecture today. Same here, if you have a robot gripper that is controlled by a DC motor. Here we have all the elements that are required in that process. We have a potentiometer on one end, and you have the robot gripper that is supposed to grab that cylinder on the other end. So you turn the control knob to determine, let's say, how much force we want to apply, or how much displacement we want the gripper to exert on the cylinder. Here is a good example where overshoot may damage the system. If you're thinking about displacement, and let's say the system takes, the gripper has to close by 5 millimeters in order to grab that cylinder. If the system happens to be a underdamped system, what is going to happen? It's going to go beyond 5 millimeters, maybe 6, 7, plastically deform the cylinder before it moves back to its final position of 5 millimeters. That was the desired position. So if this system is a second order underdamped system, we may see overshoot, and this overshoot in this particular example may damage the object we are trying to grasp with the gripper. So to be able to properly control systems like that, we need to pay attention to two things: the steady state and the transient periods. We covered both of them. So the steady state, we can use the final value, and the transient, we saw how to characterize it in the last lecture. We know that it depends on the damping ratio, and depending on the damping ratio, we can go from exponential waveforms to combinations of exponential and sinusoidal waveforms. We can even, depending on how the damping ratio is, have systems that oscillate and never settle, or we could also have systems that are unstable and whose output simply blows to infinity. So the idea now is to look at these systems. We know how the damping ratio can create this type of response, but the idea now is to quantify these signals. What can we say here? We can say that there are two different responses, the transient and the steady state. The question now is, where does the transient end? Where does steady state begin? This is something we could measure. We can call this the settling time, which is a function of omega n or a function of zeta. And this settling time is something we'll be able to control by changing the damping ratio of the system. What else can we quantify here? We could, for example, look at how much the system will overshoot before it settles at its final value in a steady state. What is that bump there? How much is it? What does influence that thing? It's something you can quantify as well. How much time does it take to first reach the steady state level? And what is this peak time, for example, where does it occur and how much is it? So all these things, these measures of performance, is something that we can now determine and derive them as a function of omega n and zeta, the damping ratio and natural frequency. So let's jump right into it. So here we have a first order system that is controlled using a feedback loop. And what I mean by that is this is our system. This is the system we want to control. This is the plant, is the physical system we modeled. And here we have its output going right like that. And we have a desired input R of t, R of s. Now, what do we do here? We are taking the desired input, comparing the desired input with the output, creating an error signal. This error signal is multiplied by a gain, k, and then the result is given to the plant. For example, this plant here could be, I don't know, could be a DC motor. And we want, let's say we want to control the speed of that DC motor. What we would be doing is to have a desired speed, R of s, compare that with the current speed of the motor, multiply the error between the current speed and the desired speed by a value of k, and then the result here could be, for example, the voltage we are giving to the motor to control its speed or position. If it is the position, this makes it easier to understand actually. If R and Y are the same, that means that we are at the desired position we want. So no voltage is required to the motor. We can simply have V of s equal to 0, and that's precisely what we get here, because V of s is simply R minus Y times K. So if R equals to Y, the voltage is 0, the motor doesn't move, it doesn't have to. Now, if we are, say, 5 millimeters away from the desired position, then the error is 5. We multiply 5 by K, that's the voltage we give to it, and then the voltage will make it move, and eventually this error is decreases until it is hopefully eliminated. So this is a very simple form of feedback control, where we have here the plant, and this is a parameter that now we can tune depending on how we want the system to behave. So basically, we are controlling the error. We are making the action. We are making the input of the system here proportional to the error between its current position, between its current state and its desired state. Okay, so now let's see how K will affect the response of this system. It's a first order system, 1 over tau s. Tau is simply a time constant, or simply a parameter in the system, I should say. And if you find a closed loop transfer function y over r, you remember how this is done. Y of s over r of s is simply k over tau s divided by 1 over k over tau s. And when we simplify this, that's what we get. That's where it comes from. Now you notice here that a k made it to tau over k, to now the coefficient of s. And this value here is what we call the time constant of the system. Now the parameter that we just added to the system as the control signal k now influences the time constant, influences how fast this system responds. And this makes perfect sense. Because if k is high, then the input given to the system is more aggressive. A small error results in a large control signal given to the plant. So the faster it should react. If k is small, then you have to let the error increase over time for that a control action to be significant, multiplied by the value of k given to the system as an input. Right? So the greater the value of k here, if you look at the block diagram, the faster the system should respond, because the more aggressive we are at correcting errors, any error. And that's precisely what we see in the transfer function. The time constant is inversely proportional to k. Right? So it will determine how fast it reaches a steady state. But to actually quantify this, we need to use our standard input signals, which in this case are the ramp and the step input. So if you give it a step input, this is our transfer function. Simply multiply that by 1 over s. Here's the inverse Laplace transform. What do we see? Well, nothing new, really. We just see that the time constant now is dependent on k. The greater k, the faster that exponential decays to 0. So that will influence the transient response. If you give the system a ramp, now r of t becomes t. The inverse Laplace is 1 over s. And when you take the inverse Laplace transform, this is the result. We see again k affecting the transient response there. The greater k, the less transient we see, the faster the system responds, because the exponential decays faster. So now let's take these two expressions and plot them. We did this in the past lectures. The only difference is now we have control over the time response. Before it was fixed, it was part of the plant. Now we are controlling the plant using a gain. And we see that we can now change how fast the system responds by controlling that gain. We see what happens here as k is increased. The time response indeed decreases, the system reacts faster. That's for the step. And for the ramp, you see the transient there getting smaller and smaller as k is increased. So with this simple analysis, we can conclude that this value of k in a first order system decreases the time constant. The higher k, the faster the response. We are directly affecting how the system reaches a steady state, how much time it takes to reach a steady state. So in theory, everything is fine. The higher k, the faster the system is. What then is the physical, is there any limit for k in a first order system? We see that at this problem in the first order system here, we cannot make the system unstable so long as k is positive. The poles are always on the left side of the S-plane. They're always negative real numbers. We can't make the system unstable. So what limits the k, or this value of k? Any ideas? In theory, nothing. Mathematically, there is no limit for k, but in practice, there is. Any ideas where that comes from? Let's go back to the free-bodied the block diagram here. If k is something that determines how much voltage we are applying to the motor in the example we used, then k must have a finite value, because there is just so much voltage we can apply to this motor. Let's say we use a system that has a maximum and minimum voltage of 24 volts, plus minus 24. So if K is, let's say, 10,000, a small error will result in a voltage of, let's say, 100 volts, 1,000 volts, which is physically unattainable. We can't apply that to the system, right? Because you're limited to plus minus 24. So the value of K is limited by the hardware, not mathematically, but physically by the implementation. It's useless here in this case to put a very high gain because it simply can't create an input to the system that is as high as we want. So this is for the first order system because we know that the first order system cannot be made unstable in this particular case. Whatever value of K we have here, the pole is always minus K over tau, always minus K over tau for positive values of K. It's always on the left side of the S-plane. It's always stable. But we need to consider also the physical capabilities of the system in order to determine this maximum value of K. This is not the case for a second order system where things are a bit more complicated because you're now shifting poles around. The poles may go to the unstable zone. So let's complicate our analysis and look at second order systems now. But before we go there, are there any questions regarding the first order analysis? No? No questions at all? Okay, so if there are no questions, I'll move on. So now let's replace the system that we were studying with a second order system. We see here S times S plus A, so that's S squared plus AS. That's now a second order system. We can find the closed loop transfer function. This is simply K over K over S plus A divided by 1 plus that. And when we simplify this function, we have the equation here. Relation between the input and the output. The structure we have for this block diagram is precisely the same. We are creating an error function. This error is multiplied by a value of K, and that determines the input to the system. So the transfer function we got now is K over S squared plus SA plus K. And if we write this in the standard form, that's what we get, omega n squared divided by S squared plus 2 zeta omega n plus omega n squared. And from this, we can determine the value of omega n, which is now K square root of K. And you can determine the value of zeta, which is zeta is A over 2 omega n, 2 zeta omega, yeah, 2 over square root of K. Now we see here interesting things happening. We see the damping ratio is directly a function of K, and the and omega n, the frequency of oscillations, is also a function of K. So let's look at the values we got here. Now we have a problem to some extent because we see that the damping ratio is directly proportional, inversely proportional to K. The greater K, the smaller the damping ratio. What is that telling us? That if you change K, we may go from an overdamped to underdamped system. The greater K, the more underdamped the system becomes. So we shall see more oscillations happening. And that's also what omega n is telling us. The greater K, the greater the frequency of oscillations. In the other case, it was easier because the greater K, the faster the system was. Now, the system might be faster, but now the system is subjected to greater oscillations. C omega n is a function of K. And the damping ratio is inversely proportional to K. Right, so the greater K, the closer we are getting to the imaginary axis with our poles, the more oscillations we will see, the more transient we'll see. here is the proof of that. So the natural frequency, the damping ratio are both functions of k. If you take the second order system and assume a underdamped system, that is the case for zeta between 0 and 1, the time response is what we see there is y of t for a step input. That's only valid for zeta between 0 and 1. Right? Only valid for a underdamped system. Now, what do we see in the time response there? We see omega n is there, and we see zeta also showing up. And they're both functions of k. So we see now we are basically changing the behavior, completely changing the behavior of the system, because now zeta affects, zeta and omega n are all functions of k. By changing k, we change the response of the underdamped system greatly. But we still need a way to quantify how that actually affects the response. So here is one example. So equation 1 is the time response of the function, is time response of y of t for a input, a step input, and only valid again for zeta between 0 and 1. But if zeta is greater than 1, then we go back to a overdamped system. And that overdamped system has an exponential response. So for large values of k, now we have, remember, zeta is a, which is a constant, divided by 2 square root of k. So greater, if k is large, we see that zeta may be greater than 1, and then we have an exponential response. Now let's start to increase k, and as we increase k, we see the damping ratio decreasing, and then we start to see some small oscillations. That's that case there. And as we keep further increasing k, the damping ratio decreases even more, and then we see more oscillations happening. And now we can completely change the behavior of the system. It was overdamped, now it's underdamped, and even when it's underdamped, we can see more and more oscillations by keep decreasing the value of k. And you see what is happening to the poles here. The pole for the overdamped system was here. Then we kept increasing k. Actually, I'm going to erase these guys here because they are too close to one another. We can't really see what is happening. And as we keep increasing k, these poles will break away from the real axis. They become complex conjugates. And that gives the second response here. And as we keep further increasing k, then the poles keep moving. And in this case, they are moving closer to the imaginary axis. And that's why we see more oscillations happening. So the poles will tend to go that way. And as we further increase k, it will further approach the imaginary axis. And when it touches the imaginary axis, then the exponential disappears and the system oscillates indefinitely. Okay. So now we need to be careful. In the first order system, things were easy, were simple, but now we are completely changing the behavior of the system by changing the value of k, by changing its transient response. Any questions? Any questions so far? Anything in the chat? No. Okay, so if there are no questions, I'll move on. So now this is, we need these measures of performance to characterize the response of all the systems you're studying. So here is the one generic time response for a underdamped system. And you can identify here a few things. We can identify the final value, which here happens to be 1. I want the system to settle at 1. This is the second order underdamped system. And you can see there's some overshoot. So the overshoot will be defined as how much the system exceeds the steady state value, which in this case is 1, before it settles. So that's one thing we can quantify, is how much it goes beyond the final value before it settles. This will occur at the peak time. We can call that TP. Yeah, so we have TP, the maximum value of the output, and the overshoot is basically this difference here. We also have what we call the rise time, which is TR, is how much time the system takes to first reach the first cross the steady state value, which is seldom used in most control systems applications, but in certain applications this is useful, especially if you have like wind tunnels or room with temperature control. We probably want to know how much time it will take to first settle, reach the temperature we want, even though it oscillates a little bit later before it settles. What else can we quantify here? We can quantify the settling time. And the settling time, in this case, is TS, is how much time the system takes to stay within 2% of its final value. It's how much time the system takes to stay within 2% of its final value. So if the final value is 1 plus minus 2%, that's this delta here, 2%, is going to be 1.02. So 1.02 and 0.98. We want to know how much time the system takes to enter a zone where it doesn't go beyond plus minus 2% of its final value. And this particular example here, that's TS, is right there. Some textbooks will use 5%, some will use 3%. Let's stick with 2%. All right, so here, because we are dealing with 2%, we want to know how much time the system will take to reach that zone of 1.2 and 0.98 and stay within that zone and doesn't go beyond that anymore. Okay, so these are the metrics, the metrics we can use: rise time, peak time, and peak value, settling time, and of course the percent overshoot. We'll be focusing on percent overshoot and settling time, but the other metrics are also important in other control systems and other fields. Any questions about these metrics? No? Oh, okay, so now that we have these metrics, we need to find a way to calculate them. So let's start with the percent overshoot. So for a unit step input, the percent overshoot is MPT minus FV divided by FV times 100. So what are we doing here? MP is the peak value. FV is the final value. So we are looking at, if you're looking at a system like this, this is FV, this is MPT, and we want to calculate this distance. That's MPT minus FV, and then you divide that by FV just to normalize everything. And then you multiply that by 100, that gives us the percent overshoot as a percentage of how much it goes beyond the final value. So if the final value is 1, and if the maximum value is 1.2, then the maximum overshoot is 20%. We go 20% beyond the final value. How do we find that value? Well, to find that value, we need to know the peak of the function, the maximum of the function. To calculate, sorry, we need to know when the maximum value of the function occurs, to then calculate that maximum value and then use that in the formula here. So if you go back, we are dealing with a underdamped system. So we can take this equation here. If you want to find the maximum of this equation, what do we do? How do you find the maximum of a function? Exactly. Take the derivative of the function and then equate that to 0. Now, why is that? Because the derivative is basically the slope of the function. If you want to know the peak value will occur over here. and the slope at that point, which is the derivative of the function, is 0. So we're going to take the derivative of equation 1 and equate that to 0, again, to find the peak of the transfer function here, the time response. So when we equate that to 0, what we can solve for is the peak time. We are taking equation 1, the derivative, equate that to 0. The only variable left there is time. So if we find the time that satisfies that equation, that time is the peak time that is given in equation 3. And now if you now want to know what the value of the function is at that time, that is given here, simply evaluate y of tp. I simply plug in back in the equation the value of the peak time. And the result of this is equation 4. This is the magnitude of the function at its peak time where its derivative is 0. Does that make sense? Yeah? You have a question from home? Anybody? No? I see somebody with a hand up here. It says just an accident. Okay. Well, we can, if you have questions at home, feel free to ask it on the mic. We'll hear you here in the hall. Now that I have the maximum value of the function, we can take this maximum value, put it back into the definition of the percent overshoot. For a unit step input, the final value would be 1. We can now calculate the percent overshoot by using this formula. And what do we see here? We see the percent overshoot being directly proportional to zeta. The increases as zeta decreases. This is given in percent. So I'm asking you to find the value of zeta for a 5% overshoot. PO is 5. It's not 0.05 because we already multiplied it by 100. So don't make that mistake. Another thing here that is prone to confusion is the fact that this was derived for a underdamped system. So this is only valid for zeta between 0 and 1. Let's go back to the equation here. This equation is the equation for a underdamped system. It cannot be used to determine a percent overshoot elsewhere of the range between of zeta between 1 and 0. So if I ask you what is the maximum, what is the value of zeta that results in no overshoot, this equation doesn't hold because no overshoot implies zeta greater or equal to 1. And this equation, once again, is only valid for zeta between 0 and 1. And despite the fact that I've always warned about this, I'm 100% sure that I will see this mistake in the final exam. This function is only valid for zeta between 0 and 1. Okay, so that's how we calculate now the percent overshoot. Any questions here before we move on? No? You can type the question in the chat if you don't want to speak. Okay, so hearing none, I'll continue. Now let's look at the settling time. We are again dealing with a second order underdamped system. So that's the type of response we should see to a step input. Now we define the settling time as the time the system takes to reach 2% of its final value. So we want the system to be within 2%, which is 0.02 of its final value. Now let's look at the time response here. The time response has a constant one that comes from the step input. That's where the system is going to eventually settle. And we have a exponential times a sinusoidal. So the sinusoidal waveform is always there as t tends to infinity. But what is happening is that we have an exponential component here that is decreasing over time and making that go to 0. So what is actually controlling the magnitude of the output is not the sinusoidal input, is not that 1. What is, excuse me, what is changing the transient, the transfer function, is actually this part here, is actually the exponential part. Everything else is constant, but this is what is changing over time. So if we want our system to be within 2% of its final value, we need the exponential component to be less than 0.02. Right? This other part here, we have no control there. It exists for time tending to infinity. It doesn't go away. So what is happening here is we are oscillating around 1, oscillating because of the sign, but the magnitude of the sign is controlled by the exponential. So if we make the exponential smaller than 0.02, we are sure that we are within 2% of 1, 2% of the final value. Does that make sense? Yeah? Sort of? Okay. So in order to then find the settling time, all we have to do is to take the exponential component, equate that to 0.02, and then find the value of t. Let's call this TS, capital TS, the settling time, and then solve for it. And when you solve for this, it's easy. You can just take the natural log of both sides of the equation. We can see the equation here giving us omega n zeta times TS is approximately 4. We can solve for TS, and this is what we get: 4 divided by zeta omega n. 4 divided by zeta omega n. We can see that the settling time is inversely proportional to omega n and to zeta. So if we increase zeta, the system will settle faster. It would take less time to reach a steady state. If increase omega n, is the same. And as we decrease omega n and decrease zeta, the system oscillates more before it settles, and therefore the settling time is higher. We can introduce. Yep.
The video quality just got super bad all of a sudden. I can barely read what's on the slides, and it seems like people in chat are saying the same thing.
Okay. That's interesting. Yeah, it must be the internet connection here. There's little I can do about it. Let me see if this. I will just restart. On my side here, everything seems okay. Is it still the case?
Yeah, it's still very blurry.
Okay, let me try something here. Okay, I don't think this helped. Give me 1 sec. Is this any better?
Yeah, that's much better.
Yeah. Okay. Can you guys still see the classroom and the PowerPoint?
I can only see what your screen sharing. I can't see your video anymore.
Okay. Okay, so let me see. Is it back to normal?
It's blurry again.
Blurry. Okay,
Yeah.
so I'll just share the screen then, and let's just stick with that. So I really don't know what is happening. If this is okay, we can continue this way today.
Yeah, that's good.
Yeah. Okay. All right. So here with equation 7, we can also define what we're going to call here the time constant for a second order system. And you're going to define this as 1 over omega n times zeta. That's the time constant. If that's the time constant, then the settling time is 4 times the time constant. And you may ask, well, where did you get this definition of the time constant? Did you just come up with that? Well, you notice that a zeta omega n is the real part of the pole, isn't it? Zeta omega n is the real part of the pole. And we are saying here that the time constant is inversely proportional to the real part of the pole. Does that make sense? Inversely proportional to the real part of the pole. The real part of the pole is what gives the exponential. So if you want the exponential to decay fast, we want the pole, we want the time constant to be, in this case, smaller. Right? So the exponential decays faster, decays fast. Let me try to explain that a bit better with this. So if you take that characteristic equation, we find the poles. We see here negative zeta omega n, negative zeta omega n. That's the real part. And then you have the imaginary part over here. If the settling time, if what dictates how fast something decays is the real part, then it makes perfect sense to say that the time constant is directly proportional to that, or inversely proportional to that. If you have a pole placed over here, this is zeta, negative zeta omega n, that's the real part, and you have the imaginary part. Depending on how close it is to the imaginary axis, same thing we saw for the first order system, the farther it is from the imaginary axis, the faster the system responds. So the greater zeta omega n, the farther it is from the imaginary axis, the smaller the settling time. So by defining the time constant as the real part of the pole, this is now in perfect agreement with the observations we made for the first order system. The closer the real part of the pole is to the imaginary axis, the slower the system is. And the greater the real part of the pole, the farther we are from the imaginary axis, the faster the system decays, because the exponential has a coefficient on top. The exponential of time times that a coefficient is larger, makes the time constant, make the exponential decay faster. Decays faster. Okay, so the time constant now is inversely proportional to, excuse me, not the time constant. The settling time is 4 times the time constant, and the time constant is 1 over the real part of the pole. So the settling time is inversely proportional to the real part of the pole. The farther we are from the imaginary axis, the faster the system reaches a steady state. Okay. All good? Yeah. Here is one example. So in this function here is a second order function. If you find damping ratio, see that this is smaller than 1. So this is a overdamped, underdamped system. And when we find the real part of the poles, and we find zeta, when we find zeta and omega n through the values that we saw here, we can calculate the time constant. And the time constant is 1 over zeta omega n. According to the calculations we did before, the settling time is 4 times tau, 4 times the time constant, which means that 4 times 2, 8 seconds is how much the system is going to take to stay within 2% of its final value. And let's see if that is the case. Here is the time response I plotted with MATLAB, and the time constant is 2. So we have here 1 time constant tau. Here we have 2 times constant 2 tau, 3 tau, and 4 tau. And you can see that indeed, after 4 times the time constant, the system is within 2% of its final value and doesn't go outside of that range. Okay. If you want to calculate this percent overshoot, all we need is the damping ratio. You can plug this into the equation 100 exponential of minus pi zeta divided by square root of 1 minus zeta squared. Okay. So that's what the settling time tells us. Okay. So let's go back to the poles we found for the second order system. This is S1 and S2, not S1. And let's plot that on this real and imaginary S-plane. So we have a imaginary part, negative sigma omega n. And then we have the real part, and you have the imaginary part, which is omega n square root of 1 minus zeta squared minus omega n square root of 1 minus zeta squared. J there is just the coordinate, is not part of the imaginary component. So you have one pole here and one pole there. Same zeta omega n, same real part, different imaginary part. What is this distance here? How do we calculate this distance? Let's call this distance d. What is d? Simple trigonometry is the square root of the real part squared plus the imaginary part squared. So d is square root of this plus that, all under the square root, 1 over 2. What you get here as a result, we have d equals to omega n squared zeta squared plus omega n squared 1 minus zeta squared, all under the square root. And then we see omega n times 1 omega n times 1, and you see, omega n squared times 1 and omega n squared times negative zeta squared. So these two terms here will cancel out. And we are left with square root of omega n squared. D is omega n. So the distance of a pole to the origin of the S-plane is the natural frequency. The distance of a pole to the center of the S-plane is the natural frequency. What else can we say here? Let's look at this angle. Let's call this angle theta. How do we calculate theta? Theta is just trigonometry again, this divided by omega n. So that is omega n, sine of theta. I forgot to ask you how to calculate theta. Well, we need a trigonometry identity. Let's go for the sine of theta, which is zeta omega n, this distance, divided by omega n itself. So omega n cancels out, and theta is sine minus 1 of zeta. So this is to say that when we place a pole on the S-plane, each pole has its own natural frequency and has its own damping ratio. And those are given by how the pole is located. The farther it is from the imaginary axis, the greater the natural frequency. The smaller the angle between the line that connects the pole and the origin is, the more oscillations we see, because zeta is now depending on that angle. So for small values of theta, small values of theta is small values of zeta. For larger values of zeta, then the angle increases, and we tend to push the damping ratio towards 1, and that's where the pole now is very close to the real axis. So the smaller the damping ratio, the smaller that angle, the closer we are to the imaginary axis, the more oscillations we are going to see in the time domain. Remember that in the example we saw before, omega n and zeta are all functions of k. So depending on the value of k, we are making now poles that were, for example, we started here, move to close to the same point. Past that point, they break away, and they start moving towards the imaginary axis. And that's all depending on the value of k, that a control gain that we saw in the example we had before. Right? But by placing a pole anywhere on the S-plane, we are now determining exactly the time, what kind of time response you're going to see, how much overshoot it has, how much settling time it will take. We don't even need to calculate the inverse Laplace transform. All we need to know is where these poles are located. And so long as you can find the distance of the pole to the origin and the angle between the pole and the imaginary axis, that is sufficient to determine the entire characteristics of the time response. So here is a summary of that. And depending on where the pole is, or depending on the value of zeta or n omega n, we have distinct behaviors here. Overdamped system, zeta equals to 1, it was supposed to be critically damped. It's missing in the second line there. So this is critically damped. We can have complex conjugates, we can have purely imaginary numbers, and we went through this before. So depending on zeta, we have different time responses, but now we can take this one step further because depending on zeta, we know where the pole is located. We can estimate this angle, we can estimate this distance, and that's all what matters to determine the time response. And in this case here, the poles are coming together as zeta is decreasing. They get to the point where zeta equals to 1. That's a critically damped system. Past that point, they break away from the real axis. They become complex conjugates, and then they start their journey towards the imaginary axis. And when they reach the imaginary axis, as k is continued to increase, is still increased, and zeta decreased as a consequence, we touch the imaginary axis. That's the undamped system, purely imaginary poles, oscillations, no exponential. Past that point, the system becomes unstable, which wasn't the case for this first order system. We could never reach the unstable zone, but now we can. Right? If any of the poles now have a positive real part, that is sufficient to bring the entire system to instability, because at least one of the exponentials in the time response will grow to infinity, and that brings everybody else to infinity as well. Okay. Any questions? No. Okay, so let's do some exercises then. Let's start with exercise 1. Now from exercise 1, I'm going to do this a bit differently. I'm going to do this the hard way, or not the hard way, the long way, using the same derivation we saw before. Then let you use the concept of the formulas later to verify the results. All right, so let's assume that we didn't have those nice formulas for percent overshoot and settling time. We are going to calculate this by hand to determine the percent overshoot. Later, just plug this in the formula to see if you get the same result. But you don't need to do it the way I'm going to do it. You can use the formula. I just wanted to use this to explain how the formula was derived. So you have a feedback system with a negative unit feedback loop. And this is the loop transfer function. We are asked to determine the closed loop transfer function, the time response for an input, step input r of t equals to a, the percent overshoot of the response, and the steady state error. Okay, so first thing to note here is that we're giving a feedback system with a negative unit feedback loop with this transfer function in the loop. So what do we have? We have a unit feedback loop. The function here serves as the main loop function. And I'll have to feed back the input. This is unit because the feedback there's no function in it, and is negative because the sum there is negative. So we have R as the input and Y as the output. The first question is to find the closed loop transfer function. So this is easy. We have y of s divided by r of s. That is 2s plus 8 divided by s plus 4, all divided by 1 plus, because it's a negative unit feedback loop, s plus 4. And this simplifies to, this is simple math. I'm going to give you the result here, s squared plus 6s plus 16. Let me know if you want me to go over this derivation, or can we just stop here? Is it fine? Yeah? Okay, so that's the closed loop transfer function. Let me just write it here. Okay, I already have it there. All right, anybody need more time? No, okay. So now we are giving this system a step input of magnitude A. Here it is. That's what it is. Okay, and we are asked to calculate the time response. So what is the time response of this? Well, the system itself is here, and it's just given a step input. So you can put this in the standard form, omega n squared divided by s squared plus 6s plus 16. Sorry, I'm just rewriting the same thing, plus 2 zeta omega n s plus omega n squared, and you can find omega n and zeta. So what is omega n? Omega n squared equals to 16. Omega n is 4 radians per second. And then we have 2 zeta omega n equals to 6. Zeta is 6 divided by 2 times 4. And this is 3 over 4. Okay, so this is smaller than 1. As this is smaller than 1, the system is underdamped. What is the time response? Let's do this. Let's do the time constant. The time constant tau is 1 over, oh, it's not showing. Sorry, I meant. Yeah, that's times. So this is 1 over zeta, which is 3/4, and times omega n, which is 4. So it's 1/3 of a second. And what is the settling time? Settling time is 4 times that. 4 times 1/3 seconds. We can calculate through this the percent overshoot by simply plugging the settling time into the equation 100 exponential of negative zeta times pi square root of 1 minus zeta squared. I don't have the result of that calculation, but it's a simple calculation, and we should find the percent overshoot. That is for 1/3 would, I don't know, I had to calculate it. Around 30–40% would be my guess. Okay, so then you may ask me, well, the equations we derived this from didn't have any zeros. This one has a 0 at -8. How does that affect the response? Well, it does affect the response, but not too much. So you can assume that this is still valid there. And so you're basically just plugging and playing this into the equations we calculated. So now let's do the same thing. But let's do the same thing without using the formulas. Let's go back to the original formulation where we got these equations from. And then let's do it that way. So I'm going to erase this. And another way to calculate everything we did is just to go back to the time response, take the derivative of it, and so on. So if you take this equation, let's say A is 1 is a unit step input. We can do partial fraction decomposition. That becomes 1 over s minus s plus 4, s squared plus 6s plus 16. And now we can do the inverse Laplace. I'm going to just give you the result for the inverse Laplace here. Y of t equals to 1 minus 1 over that. And do the inverse Laplace. Okay. Now, if you want to find the percent overshoot, we have to plot this function, and we know that it settles at 1, like that. We need to find the time, the peak time where the maximum occurs, and then calculate the maximum value of the function there. How do we do it? Well, we have to take the derivative of y of t with respect to time and set that to 0. We are calculating basically the slope of this transfer for this function, and the slope at the peak time here is 0. That's where it comes from. And you notice that when you plug that into the time response and take the derivative, equate that to 0, the only variable there is time. We can solve for that time. I'm not going to go through that because it will take too much time, but if you solve for t, we have the peak time Tp as 1.003 seconds. And what do we do with this? Well, now we want to determine the maximum value of the function. Let's call this y max, which is over there. How do we find y max? Well, simply evaluate y at Tp. That's y of 1003. And it turns out to be 1.035. That's the value of the peak. And now what is the percent overshoot? The percent overshoot is how much we exceed the final value. The final value here is 1. So we can calculate the percent overshoot as the maximum value of the function, 1035, minus the final value divided by the final value times 100. And this is 3.5%. Okay, so this is I would say the long way, the hard way. What we did before in the lecture part when we were going through the theory was to use this to determine that equation 100 exponential of for the settling for the percent overshoot. It comes from this. Now you don't need to use this every time because you see, you have to take the inverse Laplace, you have to take the derivative, you have to equate that to 0, solve for this, solve for that. All right, so we have already done that. We know that this holds for any second order system, so long as the damping ratio is between 0 and 1. So you can just plug in the original equation, but that original equation comes from this steps here. Okay. Okay, so any questions? Any questions about it? All right, so let's do exercise 2. The other ones, the C and D, I'll post the solution for them later. They are relatively simple. Let's do equation. Let's do exercise 2. So here we have, again, the same sort of structure. We have a second order system in a feedback loop with, again, K. So now we have control over K. The question is calculate the steady state error for a ramp input. And the second question is select K that will result in 0 overshoot to a step input. Calculate the steady state error for a ramp input. So R of t equals to t, and R of s equals to 1 over s squared. And select the value of k that results in no overshoot to a step input. All right, so let's do that. So let's start with the steady state error. So we are applying a ramp input to the system. R of s is 1 over s squared. Where is the error? Well, the error is right here. Is the difference between the desired input R and the actual output Y. Before we do that, we need to now define, so let me write here, error is R of s minus Y of s. We know what R of s is, we need Y of s. And to find Y of s, we need the transfer function. So what is the transfer function Y over R? It's 1 over ss plus 5. Sorry, k divided by ss plus 5. I'm just multiplying these two, divided by 1 plus that. And if you solve for this, we should get k divided by s squared plus 5s plus k. So that is the transfer function y over r. We can now find y of s by simply multiplying both sides of the equation by r of s. And now we can go back to the definition of the error and replace it in there. Now let's go back to the error function. And the error is simply R of s minus k over s squared plus 5s plus k, all times R of s. That comes from here. We can factor out R. This is R of s times 1 minus k s squared plus 5s plus k. Now this is the error for all times. How do you calculate the steady state error? We can find the inverse Laplace, but send time to infinity. But what else can we do? If you want the steady state error. In steady state, we can say that time tends to infinity. So we could use the final value theorem instead. A steady state means time tending to infinity. We can find the error in steady state as the limit when s tends to 0 of s times e of s. So this is the same as the limit when s tends to 0 of s times the error. So the error is that entire function in blue. R of s is the input, and we said that that's a step input. sorry, our ramp input 1 over s squared divided by s squared plus 5s plus k. And find a common denominator here. We have s squared plus 5s plus k minus k. Okay, see what I did there? So this r of 1 over s here square is just r of s. And then what is inside the brackets there, I just found the common denominator. So we can now multiply 1 by the denominator, and you have k minus k, that's 0. So this is equal to s times 1 over s squared. So what is left here? We are left with s squared plus 5s. Our k minus k cancel out. So now this s cancels the power, and the other s from the power will cancel the other one of the s's in s squared plus 5s, right? That's s plus 5. So the error in a steady state is the limit when s tends to 0 of, what do we have left there? S plus 5 divided by s squared plus 5s plus k, which is 5 over k. So good news here. The greater the value of k, the smaller the steady state error is. But we need to be careful because the damping ratio and the natural frequency are both functions of k as well. So as we increase k, we may have a smaller steady state error, but we will see more oscillations, and we will see more a larger settling time. Any questions here? All good? All the steps are clear? Yeah? Okay. Any questions from home? You can type it if you don't want to speak. Okay. So hearing nothing, let's continue. The next part of the question was, select k that will result in 0 overshoot to a step input. Let me write the transfer function here one more time. What was that again? K over s squared plus 5s plus k. And r of s is now a step input, is 1 over s. The question is, what is the value of k such that the percent overshoot is 0? So what do we do here? Any question? Any ideas? The question is saying, determine the value of k that results in no overshoot. So I could simply do PO equals to 100 exponential of minus zeta pi divided by square root of 1 minus zeta squared, and equate this to 0, right? Does that work? Question says, what is the value of k that results in no overshoot? We know that a k, it will influence zeta and will influence omega n. So I can simply do this, we use this function to determine the value of zeta required for no overshoot, and then manipulate k to get that value of zeta. Would that make sense? Oh, it doesn't work. Why it doesn't work? Because this equation is only valid for zeta between 0 and 1. If you want 0 overshoot, the zeta must be greater or equal to 1. So this equation does not hold because we are outside of its bounds for zeta. We can't do it that way. And the reason I'm insisting on this is that it's a very common mistake to make. So this doesn't work. We can't simply replace percent overshoot equals to 0 because that entails zeta greater than 1, and this equation was derived for zeta between 0 and 1. So here, it's not a possibility. So how are we going to fix this then? Well, if you write this equation in the standard form, we have omega n squared divided by s squared plus 2 zeta omega n s plus omega n squared. We know that to have a percent overshoot of 0, zeta must be greater or equal to 1. So for simplicity, let's say the percent overshoot will occur when zeta of 0 will occur when zeta equals to 1 or greater, because we know that we'll see later the greater value of k, the smaller the steady state error. So we want to take that into account when selecting the value of zeta as well. So we want it to have a percent overshoot, but it still give good steady state error. How do we find the value of zeta? Well, we know that omega n squared is k, and we know that 2 zeta omega n is equal to 5 by simply equating these two. So what we can do now is to determine the value of k through these two expressions such that zeta is equal or greater than 1. It's a lot easier than using the other function, which actually doesn't even hold. So from this, we have omega n equals to square root of k. And here we have 2 zeta, which is 1 times omega n square root of k equals to 5. Why is zeta equal to 1? Because we want no overshoot. So I'm equating zeta to 1. That is the limit that it will give no overshoot. So now we can solve for k. K square root of k equals to 2.5. K equals to 6.25. Okay, so for k any greater than 6.25, the damping ratio becomes smaller than 1, and the system will start to oscillate. We don't want overshoot. So we're going to go to the maximum value of k before overshoot starts. Why the maximum value? Because of the example we just saw here. The greater k, the less steady state error. So we can maximize the value of k, but we cannot go beyond 6.25, because past 6.25, we'll see oscillations, the damping ratio decreasing from getting smaller than 1, and then we'll see oscillations happening. Right? So what I did here was just to equate the standard form of a second order transfer function to the transfer function we got, and solving for the value of k that it gives zeta equals to 1. Right? We have to do it this way because the percent overshoot equation we saw before is only valid for zeta between 0 and 1, only valid for underdamped systems, which is not the case here. We want a overdamped system. In this case here, we got a critically damped system. That's good enough.